Me da mucho gusto presentar al doctor Axel de Macorra. Él realizó sus estudios de física a nivel licenciatura en la Facultad de Ciencias de la UNAM y posteriormente la maestría en la Universidad de Cambridge y su doctorado en la Universidad de Oxford, ambos en el Reino Unido. Y en la actualidad fue contratado en el Instituto de Física desde 1994, donde es investigador titular C y cuenta con los niveles más altos en el PRIDE, en el SNI y en estos mecanismos de evaluación. Ha recibido distintos premios, entre los que destacan el año pasado la medalla Marcos Moschinsky y la distinción Overseas Research Award que otorga el gobierno británico, la cual ganó en 3 años consecutivos. Ha realizado estancias de investigación en centros de alto prestigio académico en todo el mundo, y el doctor de la Macorra utiliza herramientas matemáticas mediante métodos no perturbativos para extraer propiedades fundamentales y aplicarlas al estudio de la cosmología. Con estos métodos matemáticos describe fenómenos no lineales de la naturaleza que nos permiten proponer modelos viables para la energía oscura. La producción científica del doctor de la Macorra es muy amplia, cuenta con más de 300 artículos y cerca de 20,000 citas en la literatura especializada. Bueno, ya centrándonos más en el tema de la plática de hoy, el doctor de la Macorra ha participado en el experimento que se llama Dark Energy Spectroscopic Instrument, o DESI, del cual seguramente han oído hablar mucho, desde que se planeó y es coautor de los artículos iniciales, los white papers, en 2010 y 2011, que dieron lugar a la creación del proyecto DESI. Es miembro fundador y miembro permanente de la junta directiva de DESI y, como quizás saben, DESI va a medir la posición y velocidades relativas de más de 40 millones de galaxias y quasars en el lapso de 5 años que durará el proyecto. Y esto va a permitir determinar la tasa de expansión del universo en diferentes épocas y con ello la dinámica de la energía oscura. Hoy en día DESI cuenta ya con el mayor y más preciso mapa del universo, faltando varios años aún para que se concluya, lo cual implica que se van a mejorar estos resultados. Bueno, como saben ustedes, recientemente nos va a hablar de esto el doctor de la Macorra. Se publicó este resultado muy interesante de que la energía oscura, que en la mayoría de los casos se considera una constante, está realmente disminuyendo por el tiempo. Entonces, sin más, le doy la palabra al doctor de la Macorra. Le agradezco de antemano su presencia.
¿La charla en inglés o en español?
Pues puede ser en inglés porque tenemos algunas personas.
Okay. Well, thank you for the invitation. I'm very pleased to be here with you today. And I'm going to present you the cosmological results of our experiment, DESI Dark Energy Spectroscopic Instrument. And I will show you how we can measure all these millions of galaxies in such a short time, and what the cosmological results of these great sensors Okay, this is today's Gazeta UNAM, on the front page of the Gazeta, which is talking about our DESI experiment. The only thing is missing there is DESI. But anyway, and so let me just give you a brief overview of the history of the universe. Do we have a pointer? So the universe, we don't know how it starts, but we know that in the first few seconds of the universe, there is a inflation period where the expansion of the universe grows really, really fast, and in a very homogeneous, and that is actually measured by the microwave background radiation, that the difference in temperature is 1 in 10 to the 5. After that, there is a darker area where there is no light arriving from, because there is no source of emitting light. And a few millions of years later, even more, the first stars in galaxies. The first stars are created, and then they come together, forming different types of galaxies. The universe grows in time, and then at a recent time, for whatever reason that we don't really know, but we're actually measuring it, and I'm going to give a plausible a model that can explain dark energy at the end of my talk. We have an accelerated expansion of the universe, which was a surprise to everyone. And so, as you know, the universe is very, very large, with lots of galaxies and stars. And let me just briefly show you a few of the main equations. We have the Friedman equation. A is a scale factor, and the rate the rate of A is called the Hubble constant, and through the equations of motion of general relativity, we can relate the expansion of the universe to the energy density, the curvature of the universe. We believe that K is equal to 0, so in most times this goes away. And here we have a cosmological constant, so basically is a constant which is not time dependent. The different components are actually reduced into matter, which where the particles have a slow velocity dispersion, and they evolve as A⁻�3. Radiation, they evolve as A⁻⁴, and a cosmological constant that is constant indeed. So the evolution of matter evolves as the scale factor A⁻�3. The radiation evolves as A⁻⁴, and dark energy is a constant. So we have in the history of the universe, radiation dominates in the beginning, then matter, and then dark energy dominates. In order to measure the expansion rate of the universe, we have two possibilities. One is through supernovas, which basically is a standard candle, and depending on how far away they are, is the amount of luminosity we receive. And so we can determine the distance by the luminosity. And the other one is a standard ruler, which is the Baryon Acoustic Oscillations, and that's what DESI actually measures. And it's just the standard ruler, again, depending on how far away from us is, we see it smaller, but it's still the same size. So here we have a view of a supernova that exploded in this position here. And this is our experiment. So I'm going to show you a few slides of the experiment that has measured all this number of galaxies. And what we have here is I don't know if you can actually see it. The most important part of this is there is here, right here, there's a fiber optic that we can actually not see, but there is a fiber optic here. This is a small robot, and there are 5,000 of these ones, and they can actually move. And the idea is that each fiber optic points into a galaxy, and it takes the redshift of this galaxy and the position of it. And if we have 5,000 of them, so we can take 5,000 pictures at any time. So this is a focal plane. It has 10 slices slices, and there are some different instruments, then spectrographs to measure the 5000 fibers. The spectrograph allows us to know exactly the wavelength of the light received. DESI started in 2010 to 11. There were the white papers. Then it was approved in 2014, and the construction started. Mexico joined DESI right from the beginning in 2014, and this was the first light in 2019, and that's the measurements that they actually see on this wavelength. This is the focal plane, and here we have each of these points has a fiber optic. And so this is just an animation. And so you can see, we know exactly where the 40 million of galaxies are. We know the location. We just need to measure the redshift of these 40 million galaxies. You can see the white point is the fiber optic. And so in order to make this efficient, again, we have to know exactly the position of all these galaxies before that. And so it's done automatically. Here can you see the fiber optic with just the white line. And here we will see a fly through from DESI data. And so from all this information, we have to see if there is a specific amount of galaxies at a certain distance than another wants to see if there is a departing of the Baryon Acoustic Oscillations. DESI, this is we are going to measure here is 26, 30, and even 10 more between large red galaxies, emission line galaxies, quasars, and bright galaxy survey. And this is the map that DESI has made recently. All these are also data from DESI. And so the beginning is the relationship between the acoustic scale measured in the CMB, and this acoustic scale has a certain pattern, and this pattern is translated into the position of the galaxies in the universe. And we measure this pattern in the census of galaxies today. So basically, this is like the Baryon Acoustic Oscillations happening in the universe, and the galaxies. This is again the Macorra radiation with this anisotropies are translated into the spheres of galaxies, and as long as the universe expands, these spheres grow. And by measuring the growth of the spheres, we can measure the expansion of the universe. So this is an animation. So we have the Baryon Acoustic Oscillation in the center, and here we have the sphere. But we have many of these spheres in the universe, and so they mix, and from that information, that's kind of what we see in the universe, and then measure those are the measurements of the galaxies made by DESI. And then we can make we can measure the distance between each other. And so we measure the distance from each of the galaxies. We make an histogram. This is what we get. So even though we don't see it by eye, we have an acoustic peak here at this distance, and this acoustic peak is exactly what DESI measures. And this acoustic peak is a concentration of galaxies at that distance, and depending on how far away they are, the circle, the sphere grows in time. And by measuring it, we can determine the expansion rate of the universe. This is the measurements of DESI. This is just a slide, and compared to Sloan is just was measuring only on this area that is very close to us, so redshift around 0.7, and DESI goes all the way up to the. Here we have galaxies, and here we use a Langman alpha to get information of the density before the galaxies and stars was formed. And so once again, we have the microwave background. We find these spheres in the microwave that forms actually galaxies. And so what we expected is just una caricatura, is having these spheres and having in the center a high density of galaxies, and in the spheres. The physics behind this is okay. Doesn't want. Okay, sorry. Scheiße. Okay. I'm sorry, it's not working. And so, I just said that before, this again, the correlation between the CMB anisotropies and the Baryon Acoustic Oscillations measured by the position of the galaxies. And what we actually measure is in these spheres is the size and transfer to us and longitudinal. And that gives us information about two variables. GM, which basically is the integral 1 over the Hubble parameter and the Hubble parameter, so a different redshift. And these spheres, again, are redshift dependent. And so we measured, again, a different redshift. And here are the equations, if you want to see it. This is, as I said, the dm is basically just the integral. The integral of the Hubble constant, dh is just 1 over h. And here is the lambda colored matter value of h for a lambda colored matter model. And by measuring these quantities dm and dh, and in DESI we used to divide it into a fiducial cosmology just to make see the difference between these two sizes, and it's easier to recognize if they're large or not from the fiducial cosmology. And this one here, which is called the overall value, which measures the 3 different radius of the sphere, and this one measures the quotient of these 2 quantities here. And we encoded the information of this concept in the universe in these variables. And here is the expansion rate of the universe of TV, which incorporates the three positions, and we can see the different points. And this is just this is the integral of the Hubble constant divided by the Hubble constant, and we can see the different theoretical predictions and the measurements by DESI. Let me oops. Let me just show you, I'm sorry about this. ¿Cómo reduzco aquí el tamaño?
Okay.
Okay, gracias. Okay. So this is the.
We have to share this one as well.
Yes.
This one, right?
Yes.
Perfect.
And
Was PowerPoint, right? Or PDF? Ah, okay. This is the.
yeah. So this is again measurement made by DESI. The DRT is data release 2, which means 3 years of observations of DESI. Once again, this is the number of galaxies that we have measured in year 2 is 14 million, and we had already 6 million in year 1. So it's around 20 million galaxies. The different types of galaxies, we're measuring 13 million bright galaxies, 8 million luminous bright galaxies, emission line galaxies, and quasars. And once again, we start from the CMB, and through time we have this galaxies distribution, and what we measure is the acoustic peak in the distribution of galaxies. And these are the parameters that I was talking about. DM is the integral of Hubble constant. Dh is just 1/h. And here are the results, but let me show you the results between the fiducial cosmology or the best cosmology of this average radius of the 3 directions. And we can see DESI DR2, which is the solid points, and DESI DR1, which had less than 1 million galaxies in open circles. And we can see that the precision of DR2 is very much better, which is understandable because we have more information. And here is the bow distance. Bow distance is again divided by the visual quantity, and this is the the DM and DH that I've been speaking before. And so with this information,
What is the dashed line?
the dashed line is the result for Black 18 lambda quarter matter model. So there's a large discrepancy between lambda quarter matter and the DESI data here and here, and here less here. So these are I will present the results of lambda quarter matter, and with the different traces. The first one is the bright galaxy survey, and we obtain a constraint of omega matter and H naught RD from bright galaxy survey. Then this is one is for the luminous red galaxies. This is for luminous red galaxies at a different redshift. This is a combination between luminous red galaxies and emission light galaxies. This is only emission light galaxies sample and quasars and Lam1 alpha. And this is the final result of a omega matter of 0297 and H of RD of 101, which is this black area here, the combination of the different samples. And this is DR1 that was 2 years ago, and this is 02. And so we can actually see that there is a reduced area of validation, which is not surprising because we have many more galaxies sample. And here we have the probability for DOT of the amount of matter, and depending on the here is only with DESI data. Here we have included CMB, and here is supernova with either Pantheon sample, Union 3, or DESI U5 sample. And so they're roughly consistent around 0.31 around here, but there's still spreading in the value of the amount of matter. Yes?
Can I say, all the ones on the right are the supernova, type 1 supernova surveys, right?
This here, yes. Pantheon, Union, DESI U5 are supernovas. There are three different samples, indeed.
And so, with respect to your
exactly. So there is more consensus between supernova among them, and a little bit of tension with DESI.
And you're the opposite sides of the CMB.
Exactly. Oops.
So do you expect if DESI 3 were to be done, let's say, it'll move closer to the CMB measurement because DESI 2 did?
Well, how it's going to, well, it will improve indeed because we will have many more galaxies. If we'll see exactly where it's going to go, if we would know, we wouldn't be doing it. We just assume it. So, I mean, I guess there is a tendency that we expect somewhat, but I mean, it's difficult to predict.
But in the earlier graphs, it looked like most of the discrepancies were at low redshifts. Is that right?
Again?
In the earlier graphs you showed that had various parameters as a function of redshift, it looked like the discrepancies from Planck were at low redshift. Is that?
Yeah, there is a tension between there's a tension, but there's a tension between the data, and it may be also a tension between the model. So this is lambda color matter, so it's a model dependent the results that we're seeing.
That's why, could it not be peculiar motions?
it could be peculiar motions, or it could be a different dynamics of dark energy that actually helps to solve the problem. So this is the Hubble constant. This is shoes. There is a tension that has been in the last a few years, 5 years or a little bit more. Well, shoes measures at a large or around 73 H knot, and the other is CMB, and even DESI and big magnitude oscillations go to a lower value of H naught. And so I would say my intake on this is that in order to resolve the problem with shoes, we might need some extra quantity or something different in the model that allows to shoes to coincide with DESI. And some of these things could be having extra relativistic energy that at some point has a phase transition in something like that. Having extra radiation in the beginning might help to change it, but this is just a speculation. One has to work it out just to make an intelligent comment on that.
Excuse me, can you plot DESI alone? Why DESI plus BBN?
Why did they decide on this to include BBN? Because the amount of baryons, you need the amount of baryons, and you take them the baryons from big magnitude synthesis. And so this is beyond dark energy. This is well, lambda colored matter. And so this is a evolving dark energy. And what is used in DESI is these two parameters, W0 and WA, which is probably the most simple parameterization of dark energy besides a cosmological constant, though, well, one equation of state W0. W0 basically is the value of the equation of state today at present time, and WA is just the derivative of the expansion of the equation of state today. So we are measuring the evolution of the universe with two quantities which are dependent on its value today. So it's certainly not the most versatile parameterization, but it's the next step, the simplest step, easy to follow through all the pipeline and see what you get. And so this is, we can see the difference between DR1 and DR2. Here we have, this was DR1, and this again is with DR2, the equation of state, with CMB. And here we have CMB and Pantheon, and CMB and Union 3, and CMB and this Union 5. Again, all these three samples are supernovae. And we can see there's a slight difference in the contours where Pantheon gives a higher level. But all of these three important points is that they rule out at least a 2 sigma, a cosmological constant. Yeah. So before, if you assume it's a cosmological constant, you get results of a cosmological constant, and you are staying in that box. When you give a little bit of freedom, there's not much freedom, it's just the simplest thing. Taylor first order. You can see that at 2 sigma, at 95% is ruled out. Yeah. In particle physics, determination of a signal is to 5 sigma. So in CERN, this would not be a determination of saying ruling out a cosmological constant. Probably we will say it's not rule out a cosmological constant, but the information hints on something evolving in time. And that's really exciting because it opens a lot of work to everyone in cosmology Because if it's a cosmological constant, that's it, you have a cosmological constant. If it's evolving, then there can be many different models that allow you to describe DESI, and depending on this model, you will either choose one or the other ones. So it's an open question. And saying that, here we have the value of this equation of state W0 WA that I just showed in the last one, and this is evolution of the equation of state in a model that does not allow the energy density to go below -1 to be phantom. And so this is other measurements of DESI, and this is a model I'm going to present you in the next few minutes. This is again the picture here. And this is the model that we presented, which is called bound dark energy, and it's this size here. So we just enlarge it so you can see it. The area between these two is 4 orders of magnitude. Here's the equation of state. This is the evolution of our model, and this is the evolution at a larger redshift. And okay, I will come back to the model. So here are the neutrinos. We have here the values of DESI and DESI with C and B, and so they are consistent C and B with DESI, the amount of neutrinos. And here I'm showing the big box experiment. This was generated in 2010 and 2011. The name big box was previous as DESI. There were 2 different groups in the United States, and the Department of Energy told them to join together, so they changed their names to DESI. But I mean, it's exactly this experiment in the telescope. And so Mexico had a participation in DESI right from the beginning. Here we have we hosted for the second time the collaboration meeting of DESI in Cancun, and here's the collaboration, and some of us are around there, and we had a lot of people on Zoom. And okay. Let me go back to. Okay, so this is.
Do you mind if I change the sharing again?
Oh yes. I thought it was.
Nice. This window seems to have disappeared.
So this is the picture of what I just showed you in the other one. Again, these are the contours of WA for the 3 different union supernova data. And this is the equation of state again, if you don't have a phantom crossing. And so the model I'm going to present is called bound dark energy. And well, dark energy, we don't know exactly what it is. So do we have theoretical model explaining dark energy, or can we reduce the number of free parameters of lambda quadrat matrix? And what about the posterior distribution? Basically, do they have a good fit with the data or not? And so the model we have presented in bound dark energy is basically proposing that dark energy corresponds to a group SU3 with 6 flavors. And if we compare this model with the standard model of particle spaces, physics, we have an SU3, which is very similar to this one, SU2 and SU1. So the strong weak electromagnetic interactions of the standard model, which is perhaps the most accurate theory in physics, is given exactly by this formulation. And we are just including a gauge group which is very similar to the strong force, but this is supersymmetric. So the scalar particles would be dark mesons, so we have dark baryons. And the lightest particle of this group of particles we call it bound dark energy. And as in the standard model where we have lots of particles, the energy density of the heavy particles move basically into the lighter ones, and we end up having the light particles. And so here we are, this is the pion. The pion is basically made out of quarks, or the protons and neutrons, which is made out of 3 different quarks. And the scale of QCD is 200 MeVs. Similar in DTE, we have a scalar field, and the scale when this happens is much lower. It's at around 40 electron volts. So we can the equation we can measure mathematically in a supersymmetric using the Havlik-Dine-Seiberg superpotential, which is a very important mathematical result in the last 15 years. And we obtain a very simple expression of the scalar potential, which is an inverse power potential with an exponent 5 to minus 2/3, and lambda c is just a proportional constant. However, if we want to join, for example, we assume that we have the 3 gauge groups of the standard model, and we do that, and they are unified at the grand unification scale. If we assume that our model is also unified at the unification scale, we reduce the number of parameters, and then we can obtain the value of this lambda c in terms of the value of the energy density at the unification scale and the gauge conflict constant at unification scale. And this is the theoretical result of lambda c, 34 plus minus 16 or minus 11. And we can relate the energy densities of these parameters in terms of the 2 free parameters of VD models, and it's given in terms of the number of particles. This G corresponds to the number of particles of the standard model and of our gauge group, and amount of radiation at present time, which you know very well because we know the temperature of the photon. With these parameters, again, this is the parameter of the temperature of photon. The other ones are just numbers. How many particles do we have? And this is a value that we obtain, and it has basically no error, but for the temperature of the photon, which is very, very small. So running this model, we can compare here our model with a W0 WA model and lambda colored matter. And here we have different parameters. And probably an interesting point is to account that lambda colored matter has 6 free parameters. WA/W0 introduces 3 more parameters, namely W0, WA, and the amount of dark energy at present time. And our model VDE predicts the amount of dark energy today, and the evolution of the equational state is not a free parameter. It only depends on the choice of model that we do. And so if we can see from here that in VAO we have a much smaller reduced chi square in BD than in lambda quadrant matter, and even so more in W0WA quadrant matter model. And it's very similar in terms of the supernova, and it's very similar in terms of the CMB. But the reduction here is very, very large. And what I said in the beginning, this is the value of the equation of state in the model WAW0, which is basically this one here. And this is our model, which enlarged it. And again, this point here is 4 orders of magnitude than this evolution here. This is the evolution of our equation state, and this is the evolution of DESI when they allow for a phantom crossing, which means they can go below -1. And this is a sum of the equation of state evolution in our model at redshift between 0 and 3.
Axel, sorry, I don't understand.
Yes.
The bottom left.
Bottom left here?
Your model is a small vision.
My model is here.
But the data is the orange.
The orange is a W0WA model, the parameterization of the standard, what DESI is using, the model W0WA as a very large freedom. W0 is a free parameter, W is a free parameter, and the amount of energy is a free parameter, so it has a very large contour areas.
But if you put your model on the top right, where is your model?
This one here, on the top right here?
Yes.
Here is none, this is the only DESI.
This one?
All these three are only of DESI. It's not my model there.
But if you put your
No, here. This one here is this one here.
So isn't your model ruled out because it's separated from the data?
No, it's not separated. I mean, they are not consistent.
How many
I would say that this model is wrong, not mine.
I understand that one.
No, you can see in the chi-square. The reduced chi-square is when you measure exactly the goodness of fit of your model. Our model reduces it by 42%.
But where is the data?
Where's the data?
Yes.
Oh, which data? No, it comes with the CMB and DESI supernovas, different types of supernovas, and DESI data, of course. Both of them are constrained with exactly the same data. This is just the results. The wanting to see controls likelihoods of the different parameters.
So let me see if I understand. What you mean is that your model has information of the data, of the DESI data.
No, what I'm saying is my model is very constrained. It has no free parameters. It is what it is. The value is free, and that's it.
Yeah, because what confuses us,
Yes.
I guess also Susana,
Yes.
is that
Here?
if we read DESI, then we imply that there is data in that plot.
No, there's all these constraints are using the same data in the different models. Here, this is just a comparison of using W0WA in DESI and choosing DESI data and choosing in this one here is Pantheon supernovas, and this one here is Union supernovas, and this one here is this year 5 supernovas. This year 5, and so it's just showing here how the equation of states values depend on the choice of supernovas that you're taking. And so this is W0WA model. This one here is W0WA model, and this model is the bound dark energy model. And the contour values here, since it's a different model, since the evolution of it differs, in the sense that the W3WA is just a picture today. So the evolution changes, and probably maybe in the next one we can actually see it. And so here this is just a picture today. This is just a picture today of the values. Here we see this is the evolution of the equation of state as a function of redshift. And this is what DESI has. Between 0 and 2.5. And this is what we get from 0 to 3.5. Notice that here it goes from -1 to -0.7, and here it goes from -1 to -0.2. So it's basically something around here.
Yeah, I think that we just would like to see your plots on top of the data. not separate.
I don't understand what you mean on top of the data. They are constrained by the data.
No, but if you put your line on the top figure, then one can see how good your model is with respect to the data.
You mean I should have plotted this curve with this one here?
Yes.
Yeah, but it's done here somehow.
Your prediction for the bow scale compared with the bow measurements as an example. Like the first plots that you showed, like lambda CDM and the plots that you showed at the beginning, where you have the data plot points, the bow data points.
Oh, yeah.
Yeah.
This is just the posterior of them. Yes, indeed. Yeah, you're right. Yes. Yeah, I didn't put them, but yes, it's a good idea. I should. Yes, indeed. Yeah. I mean, it's usually it's just both models are using exactly the same data. It's just that one model, W0WA, is a model which is free for these two parameters. In our model, they are constrained. They are constrained by the model.
So the other models is degenerate. I mean,
W0WA is generated.
Yeah.
Well, no, it's just a Taylor's expansion at present time. Is what is the value of the equation of state today, and what is the first derivative of the equation of state today, and from that you can get a lot of information. It's the first step after saying that you have a single point, a cosmological constant with W0 equals 0 and WA equal -1 is this point. This is here. Is lambda polar matter, that point there.
Well, okay, you're saying in your model, some parameters are constrained, they're fixed. You have no freedom. The other one has some freedom, and some power has been given to those different parameters. You're constraining the same parameters on this thing.
What I'm saying is there are no free parameters in the dark energy. Of course, the amount of matter, the amount of radiation, the amount of different things which are cosmologically important in a model, we do vary them. So the only thing that we're changing here is changing the equation of state of dark energy.
So
we include the same neutrinos and the same body of relativistic energy and matter. And so the only difference in the model is how do you describe the
Are there
equation of
same
dark
number of
energy?
parameters in the two models? Are there same number of parameters?
The only difference in both models are parameters are the ones that involve dark energy. So in that sense, dark energy, a cosmological constant has a single parameter, which is the amount of dark energy in a cosmological constant. W0WA has three parameters, which is the amount of dark energy, the equation of state today, and the first derivative WA today. Our model, the way it is constrained, is the evolution of the equation of state is fixed, and the amount of dark energy today is fixed. Well, not the amount of dark energy at the beginning of the evolution is fixed, and so the value today is determined by the different parameters, but you cannot change the value. So you are not playing with different values of the equation of state.
Are you saying that if you were to add more parameters to the linear model with W0, WI, you were to add a quadratic term, then you'd expect the orange thing to converge on where your your physically motivated model is.
That's how, I would agree entirely with what you're saying, yes.
Yeah.
Yeah.
But of course, it would have a lot more free parameters, which is not good.
Yeah, but it's, yeah. Yeah, we could do a Taylor expansion of this graph and then do it, but I mean, so it's a so it's much easier to have just a single function than having to write this function in terms of parameters. Here we have the contours of the different parameters. Here we have the values of lambda c and AC, the two important parameters in our model, which corresponds to the value when the transition took place and the scale of the energy at that point. And here we have here we compare it also for WA model and lambda color matter, and there is a small tension, of course, in W0 and WA. Here we see a spread on our contours because there are other variables that in cosmology, which means all of these ones here. There are different values which I didn't plot because we are just concentrated on basically on the dynamics of dark energy. But usually in a cosmological model, you have 6 different parameters of which is the dark energy, amount of matter, the radiation, and different others, which is the standard. They have 6 different models in the simplest version. And so this is an article that we just sent to a journal with our model, bound dark energy, a particle origin of dark energy. And then I will basically conclude. DESI has measured with great precision the expansion history of the universe due to the measurements of the Baryon Acoustic Oscillations. DESI, the main goal is to determine the dynamics of dark energy, and a cosmological constant has been ruled out at 95% confidence level to sigma at this point. And we have proposed a dynamic of dark energy named bound dark energy contained within an SU3 gauge group, similar to the standard model gauge groups. Our model has no free parameters in this, and BD reduces the bound chi-square, the reduced chi-square by 42% compared to the W0WA product matter model. And well, that's it. And no, probably not. That's not it. Let me just let me just show you this. This is you just in the beginning I showed you the UNAM news, and here the different articles that have been written since May 19 last week. There's 733. This is no articles. This is news in the news. How many journals and magazines and TV, radio, etc. have show the experiment, have written up about the results. And so there are about over 1,500, around 1,500 articles, and DESI year 3, which is now, it's almost over 175,000 articles around the world with the news of dark energy not being and here basically all the news. So what I'm trying to portray with this is that it is a really exciting chance to be working in cosmology. The open question of what dark energy is clearly open, and it's a very fertile area to work for everyone. And I think there will be more surprises. We'll have better data, we will construct better the models, and we'll probably should point out what dark energy, not only how it evolves, but what the nature of dark energy is. Thank you.
If dark energy had a particle origin, do you expect it to decrease as A to the Q or not?
A to the
Q. Yeah, because.
Yeah, you would expect in this model that you have particles which are relativistic, and then when the force of this group becomes strong, binds the particles together forming bound states, which is something similar that happens with electromagnetism in the sense that you can have free protons and electrons, and then you have the atom, the stable proton electron stable. Yes.
Well, very, very, very interesting, especially your model. For those of us who aren't experts on particle physics, can you explain what is the difference then between the strong nuclear force and what you're proposing for this dark energy, given that they both have the same gauge symmetry?
I would say it's just the same, it's just a different group. I mean, in QCD, you have elementary quarks which are basically massless, and then when the temperature drops down, they bind together and forming protons and neutrons and mesons. So this group is exactly the same. So you'd have the elementary.
Having free, if we lived in a world with free quarks, then it would look like dark energy.
No, I would say dark energy is like quarks. Like quarks and neutrons, say, because they are neutral. The only difference is if you can develop a scalar potential, something that is not that you are only relativistic or you're only matter-like, which is what happens basically in the standard model of particles in terms of cosmology in a very simplistic way. But here is like, if you think of QCD, you have the quarks. Probably if it's a very, very high, you have quarks moving free in a plasma, and then you drop down the temperature, and then the quarks bind together and they form neutrons, protons, barons. This is exactly the same picture of bound dark energy as in QCD. The difference in QCD and bound dark energy is that we assume supersymmetry. With that, we allow to derive the technique was called Affleck-Hybrid, which was really, really famous a few years ago. How to derive a non-perturbative potential. And this non-perturbative potential is the one we use, and we see the evolution of this particle from that. And again,
the binding energy is a lot lower.
It's indeed exactly. So one of them for QCD was 200 MeVs, and for us it's 40 electron volts basically.
Is it a coincidence that that's sort of similar to the binding energy of hydrogen? And
no. One is 10 to the 6, and the other one is electron volts.
No, but
it's 10 to the 6 difference.
Electrostatic binding energy in the Coulomb binding energy of atoms is of all the tens of electrons.
Oh. No, that's an interesting question. I haven't thought about that. I wouldn't attempt to relate dark energy with atoms, but I mean, But yeah, that's an interesting coincidence indeed.
¿Alguna otra pregunta? Bernardo.
Would this bound dark energy be related in any way to the scalar field or of inflation?
Scalar field,
For responsible for
Más
inflation?
alto.
the last word was?
The scalar field responsible for inflation at the beginning of.
Yeah. No, at the beginning, no. No, this scalar field is like a baryon. A baryon in the beginning of the universe is there are quarks. There is no baryon. So bound dark energy is a scalar field, a low temperature, a high temperature. The particles, the constituent particles, the dark, say, quarks, would be separated, and they would be relativistic.
The new results from DESI, what they can tell us about the sigma intention?
That's a good question. I will get back to you.
There are no comments or questions. Thank our speakers then.